So today onwards we are going to start our unit 4. It is related to partial differential equations. So we are about to study a simple type of partial differential equation, that is second order linear partial differential equation, that is PDE. Okay, so if we recall, then a partial differential equation is any differential equation that contains two or more independent variables. Okay, so we have two or more independent variables in that equation, differential equation, and the derivatives in that equation are called as partial derivatives. So just we'll consider the general form of partial differential equation, second order linear partial differential equation. So if we consider it in the two variables, that is x comma y, then it is represented as a uxx plus b uyxy plus c uyy plus dux plus euy plus fu, which is equal to some another function g of x comma y. Okay, so here a b c d e f are nothing but just constants, and they cannot be all zero because we want a second order linear differential equation. Okay, and uxx is nothing but we have a function of ux comma y, and if we take second order derivative with respect to x, then we get xx. Similarly, if you have uxy, then what we can say that we have to derivate with respect to x as well as with respect to y. Similar it goes for the rest of the case. So now if you see, then this a b c, we know that the value of discriminant, that is discriminant is given by b square minus 4ac. Okay, so depending on the coefficients of the equation, you get the discriminant, and value of discriminant has three cases. So if it is greater than 0, then the equation, the type of equation is known as hyperbolic equation. Okay, so this type of equation where you get a PDE and the discriminant is greater than 0, then you can say that it is an hyperbolic equation. Similarly, if b square minus 4ac is less than 0, then it is known as elliptic equation. Okay, and the last one is b square minus 4ac equals to 0. So if this is the case, then it is known as parabolic equation. Okay, so I'll just give you some examples of each of them. So for in hyperbolic equation, we have our wave equation. Okay, so wave equation comes in the form of hyperbolic where the discriminant is greater than 0. Then where discriminant is less than 0, we have a heat function, so a heat equation. And in terms of elliptic, we have Laplace equation. We'll get into each of them in detail later on, but before that we'll just consider one example based on just general form to see, just get idea about what it is. So now if you consider one example, that is uxx equals to utt plus 6ut. Okay, so now you can rearrange this to form a normal second order form. You can just relate it to the general form. So you have 9uxx minus utt minus 6ut equals to 0. Okay, so now comparing this with the general form, you'll get instead of xy you have x and t. So instead of x you can just keep it as x, and instead of y you can substitute as t. So comparing this, you'll get value of a as 9, b as 0 and c as minus 1. So after comparing this, you can find the determinant discriminant. So value of discriminant is b square minus 4ac. So after substituting this value, its value will be b square is 0 minus 4 into a is 9, c is minus 1. So this is 36, which is greater than 0. So as discriminant value is greater than 0, we can see that the given second order partial differential equation is of hyperbolic equation. Is a hyperbolic equation. So this is a hyperbolic equation. So now let us consider what is heat equation. Okay, so if you consider a thin bar, then so next point is a heat equation or a heat conduction equation. You can see anything. So if you have a thin bar, so this is your rod or bar, something, a metal bar, and if you have if it is made up of a homogeneous material, then suppose that the side of the bar is perfectly insulated. That means the outer side, like sidewise, it is insulated, and the heat can just flow in or out from the two ends of the rod. Okay, so now the moment of heat inside the bar just occurs in the x direction. Suppose if you consider this rod in this way, so if this is your x-axis and this is your y-axis, then this heat is possibly heat can just go in and out in this x direction and not in y direction because it is insulated. Now if you consider that this one end is on the origin, okay, so here x equals to 0, and if the length of rod is L centimeter, meter or units, whatever it is, so then here value of x will be L. So you can say that 0 is less than or equal to x is less than or equal to L. Okay, so that's the condition for the length, that is x. Now what about y-axis? So x is regarding length, then y is regarding the time. So then the amount of heat content at any place inside the bar where the value of x varies between 0 to L, and we should not first include the end points because we can have a condition where the end points are immersed in ice water or something where the temperature is 0. So you can consider the end points have temperature 0 and the rest of the part contains the heat. So now, so the amount of heat content at any place inside the bar and at any time t, it is given by the temperature distribution function, which is ux comma t. So at any point x where of the rod and at any time t, value of ux is nothing but the temperature of the rod at that point at that time. So this homogeneous one-dimensional heat equation is in the form of alpha square uxx equals to ut. So you have to double derivative, take second derivative with respect to x and first derivative with respect to u, with respect to t, and alpha square is nothing but the constant coefficient, and it is known as thermodiffusivity of the bar, which is not included in your syllabus, but it's just the constant coefficient, this alpha square. So now if you consider u of, that is the temperature of that rod at point 0, so if x equals to 0, so that's the end point, at any time t it will be what, just 0, because we have assumed that the endpoints are dipped in some ice water or something so that the temperature is reduced to 0 at both the ends. So u of 0t equals to 0. Similarly, u of L comma t equals to 0. So that's for the other end. So now these two conditions are known as boundary conditions. Okay, so for any equation you'll have, or any problem, you'll be given some boundary conditions. Okay, so they literally specify the conditions which are present at the boundaries between the bar and the outside. Okay, so now in addition to that, there is the initial condition as well. So the initial temperature distribution within the bar. So if you consider u at any point on the rod at time t, so when the initial condition, so this is known as initial condition. So it is just, it gives us idea of the temperature everywhere inside the bar at t equals to 0. So you can say that u of x comma 0, which is the initial condition, will have some value f of x. So finally you can conclude to the 3 points with respect to heat conduction equation. So this heat conduction equation is given by this formula, which is alpha square uxx equals to ut. Now the boundary conditions for that equation are u of 0 t equals to 0 and u of l comma t equals to 0. So these are your boundary condition, and initial condition is this one. So such type of problem where you get the initial as well as the boundary condition is known as initial boundary value problem. So now, depending on the boundary condition as well as the initial condition, the problems or the differential equations are considered into different types. So first one we have seen that it is heat equation, so heat problem. Now the next one is Dirichlet's problem. So in this, if you are given a continuous function f which is on the boundary, so if you have certain region in heat, we had some rod or as such thing. So in this Dirichlet problem, if you have a domain R and the boundary of that region R is denoted by C, then a function f is defined on this boundary C, and u of xy as a given function. Then if it satisfies the Laplace equation, so what's the Laplace equation? It is uxx plus uyy equals to 0 in this region R, and if on the boundary of that region R we have the boundary condition as u of xy is certain function f which is a continuous function, then such kind of problem is known as a Dirichlet problem. Okay, so Laplace equation is given by uxx plus uyy equals to 0. Similarly, we had seen a hyperbolic function or hyperbolic equation. So in that we had given example of a wave function or a wave equation. So a wave equation has a form of uxx equals to c square uyy. So if you see an equation of this form, then you can say that it is of a wave function, wave equation, or it is a wave equation. So now the next one is Cauchy problem. So Cauchy problem is nothing but if you have a condition utt minus uxx equals to 0 for any t which is greater than 0, and the boundary condition is u of x comma 0, or sorry, the initial condition is u of x comma 0 equals to f of x, and the derivative of partial derivative of u of x comma 0 with respect to t is nothing but another function g of x, where f of x and g of x are any arbitrary equation, then this is known as a Cauchy problem. So if you see utt minus uxx equals to 0, a equation of this type with this initial conditions, then you can say that it is a Cauchy problem. Now if we consider this three equation, that is first one was our Dirichlet's problem, then Cauchy problem, and the heat equation. So if you have that, then these are known as well posed problems. So well posed problems are nothing but problems which have solution. So the solution exists for that equation. But now if we consider Laplace problem, so Laplace equation is nothing but, we know that Laplace equation is given by uxx plus uyy equals to 0. So if we consider Laplace equation, and so this is your Laplace equation, and if you just imply the boundary condition for the Cauchy problem, that is u of x0, sorry, the initial conditions for, or boundary conditions for the Cauchy problem, then this two together, that is ux comma 0 equals to some function f of x, and partial derivative of ux comma 0 with respect to t is some function g of x. Then these two functions, these two together will form a ill-posed problem. So ill-posed problem is nothing but a problem which does not have any solution. So the solution for that problem does not exist. Okay. So now let us consider few concepts, where first one is forward difference. So in this, if you consider, so if this is uij, where I is nothing but the value of u just moves in the x direction, and with respect to j, that means it moves in the y direction. So if you consider a certain point, so uij, then ux is given by two values. So it is by two methods. So first one is, if you consider forward difference. Okay, so for forward difference you need to have one value, that is ui plus 1 comma j. So I plus 1, that means you are moving with respect to the x-axis, so you are moving in the direction of x-axis, and plus 1 indicates that it is just by a difference of h. So there is a common difference of h after a certain interval. So if this point uij moves to the next point at the difference of h, so in the direction of x-axis, then you can see that this point is I plus 1 comma j. Okay, so this is the next point. So similarly you have one another. So next is difference, backward difference. So backward difference is nothing but, if you have point uij, and if you move in the opposite side towards the left side in the direction of y, so you move to its back side, so it is backward direction in along x-axis. So you'll get a point u I minus 1 comma j, okay, after a certain interval of h, because h is a common interval at every point. So now you got this 3 points, ui minus 1j, which is a backward point, uij, which is the initial point, and the next point is ui plus 1j. So when you use a forward point in the formula, you get the forward difference. So to find ux by forward difference, you need to have a forward point, a point which is forward to the uij. So for this you can have the formula as ui plus 1 comma j minus uij upon delta x. So this is the forward difference. Similarly, if you want to use the backward difference, you need to use this backward point. So for this you will get uij minus ui minus 1 comma j upon delta x. Okay, so these are with respect to forward and backward. Now the next point is central difference. Central difference is nothing but, so you need to use both this value, forward as well as backward points. So you can calculate ux by ui plus 1 comma j minus 2ui comma j plus ui minus 1 comma j upon delta x square. So have you got that value? You just need to have whatever ux you had partial differentiation of u with respect to x in the forward and partial differentiation of u with respect to s in the backward difference. You have to make use of this. So you have formula as partial derivative of u with respect to x by forward difference minus partial derivative of u with respect to x by um, what's backward difference. Okay, so this is backward difference upon delta x square. So this is the formula to get ux by central difference. So substituting the values of this by ux by forward difference, it is ui plus 1 comma j minus uij minus, we have to write the value of ux with respect to backward difference. So this is the value. So it is uij plus ui minus 1 comma j upon delta x square. So after solving this, you will get ui plus 1 comma j minus 2uij plus ui minus 1 comma j upon delta x square. So that's the required formula for central difference. Okay, so now similarly it goes for uy, uyy. You can see, so ui will be nothing but with respect to y. So you are taking partial derivative with respect to y. So you have to move u in the direction of y-axis. So this along the y-axis we have j. So you have to change the point of j. So this, if you consider a regular interval of k here, okay, so if it is moving by a k distance, then this next point will be ui common and this will be j plus 1. This will be your forward point. Similarly, if you go in the backward direction, then you will get ui comma j minus 1. Okay, so using this, you again have to find the forward difference, backward difference and central difference. Just make change with respect to j coordinate in this formula. So you can directly have uyy as ui j plus 1 minus 2ui comma j plus ui j minus 1 upon delta y whole square. Okay, so that was for uyy. You can find it for ui for using forward difference, backward difference and central difference. Now we had a Laplace equation. So Laplace equation was given by uxx plus uyy equals to 0. So that was our Laplace equation. So now if you consider one condition that delta x equals to delta y, then you will get uxx was nothing but, sorry, so this was for uxx, it was for uxx, not for central difference. So uxx was this formula, and for ux by using central difference, you need to just have the average of both the points. So average of both the points is nothing but ui plus 1 comma j minus ui minus 1 comma j upon 2 delta x. So this is just by using central difference, you need to just calculate the average between the 2 points, and whatever we had calculated, it was for uxx. So this is the value of uxx. So now substituting this value of uxx in this equation, Laplace equation, will get ui plus 1 comma j minus 2ui comma j plus ui minus 1 comma j plus ui comma j plus 1 minus 2ui comma j plus ui comma j minus 1. So this was the values, these were the values for uxx and uyy, and it was delta x. square which is equal to 0. Okay, so now after solving this, you can get so minus 2uii, sorry, 2uij and minus 2uij. This will get ui plus 1 comma j minus 4ui comma j plus ui minus 1 comma j plus ui comma j plus 1 plus ui j minus 1 upon delta x square equals to 0. So after multiplying this delta x square with 0, you will get just this equation which is equal to 0. So now keeping 4ui comma j on one side, so you can have ui comma j equals to, so just letting this to the other side, you will get ui plus 1 comma j plus ui minus 1 comma j plus ui comma j plus 1 minus ui j minus 1. This and this 4, if you divide this, then you'll get value of ui comma j in the Laplace equation.